A vector space is a collection of objects called vectors, which may be added together and multiplied by numbers, called scalars in this context. Scalars are often taken to be real numbers, but there are also vector spaces with scalar multiplication by complex numbers, rational numbers, or generally any field. The operations of vector addition and scalar multiplication must satisfy certain requirements, called axioms, listed below. Euclidean vectors are an example of a vector space. They represent physical quantities such as forces. Any two forces can be added to yield a third, and the multiplication of a force vector by a real multiplier is another force vector. In the same vein, but in a more geometric sense, vectors representing displacements in the plane or in three-dimensional space also form vector spaces. Vectors in vector spaces do not necessarily have to be arrow-like objects as they appear in the mentioned examples. Vectors are regarded as abstract mathematical objects with particular properties, which in some cases can be visualized as arrows. Vector spaces are the subject of linear algebra and are well understood from this point of view since vector spaces are characterized by their dimension, which, roughly speaking, specifies the number of independent directions in a space. A vector space may be endowed with additional structure, such as a norm or inner product. Such spaces arise naturally in mathematical analysis, mainly in the guise of infinite-dimensional function spaces whose vectors are functions. Analytical problems call for the ability to decide whether a sequence of vectors converges to a given vector. This is accomplished by considering vector spaces with additional structure, mostly spaces endowed with a suitable topology, thus allowing the consideration of proximity and contiguity issues. These topological vector spaces, in particular Banach spaces and Hilbert spaces, have a richer theory. Historically, the first ideas leading to vector spaces can be traced back as far as the 17th century's analytic geometry, matrices, systems of linear equations, and Euclidean vectors. The modern, more abstract treatment, first formulated by Giuseppe Peano in 1888, encompasses more general objects than Euclidean space. But much of the theory can be seen as an extension of classical geometric ideas like lines, planes and their higher dimensional analogues. Today, vector spaces are applied throughout mathematics, science and engineering. They are the appropriate linear algebraic notion to deal with systems of linear equations, offer a framework for Fourier expansion, which is employed in image compression routines, or provide an environment that can be used for solution techniques for partial differential equations. Furthermore, vector spaces furnish an abstract, coordinate-free way of dealing with geometrical and physical objects such as tensors. This in turn allows the examination of local properties of manifolds by linearization techniques. Vector spaces may be generalized in several ways, leading to more advanced notions in geometry and abstract algebra. Introduction and definition. The concept of vector space will first be explained by describing two particular examples. First example. Arrows in the plane. The first example of a vector space consists of arrows in a fixed plane, starting at one fixed point. This is used in physics to describe forces or velocities. Given any two such arrows, v and w, the parallelogram spanned by these two arrows contains one diagonal arrow that starts at the origin, 2. This new arrow is called the sum of the two arrows and is denoted v plus w. In the special case of two arrows on the same line, their sum is the arrow on this line whose length is the sum or the difference of the lengths, depending on whether the arrows have the same direction. Another operation that can be done with arrows is scaling. Given any positive real number e, the arrow that has the same direction as v, but is dilated or shrunk by multiplying its length by a, is called multiplication of e by a. It is denoted av. When a is negative, av is defined as the arrow pointing in the opposite direction. Instead, the following shows a few examples. If r equals 2, the resulting vector or has the same direction as w, but is stretched to the double length of w. Equivalently, 2w is the sum w plus w. Moreover, v equals minus v has the opposite direction and the same length as v. Second example. Ordered pairs of numbers. A second key example of a vector space is provided by pairs of real numbers x and y. Such a pair is written as the sum of two such pairs, and multiplication of a pair with a number is defined as follows: plus equals under equals. The first example above reduces to this one if the arrows are represented by the pair of Cartesian coordinates of their endpoints. Definition: a vector space over a field F is a set V together with two operations that satisfy the 8 axioms listed below. Elements of I are commonly called vectors. Elements of F are commonly called scalars. The first operation, called vector addition or simply addition, takes any two vectors v and w and assigns to them a third vector, which is commonly written as v plus w, and called the sum of these two vectors. The second operation, called scalar multiplication, takes any scalar and any vector v and gives another vector av. In this article, vectors are distinguished from scalars by boldface. In the two examples above, the field is the field of the real numbers and the set of the vectors consists of the planar arrows with fixed starting point and a pairs of real numbers, respectively. To qualify as a vector space, the set V and the operations of addition and multiplication must adhere to a number of requirements called axioms. In the list below, let U, V and W be arbitrary vectors in V, and R and B scalars in F. These axioms generalize properties of the vectors introduced in the above examples. Indeed, the result of addition of two ordered pairs does not depend on the order of the summands. Plus equals plus. Likewise, in the geometric example of vectors as arrows, v plus w equals w plus v, since the parallelogram defining the sum of the vectors is independent of the order of the vectors. All other axioms can be checked in a similar manner in both examples. Thus, by disregarding the concrete nature of the particular type of vectors, the definition incorporates these two and many more examples in one notion of vector space. Subtraction of two vectors and division by a scalar can be defined as v minus w equals v plus v, a equals v. When the scalar field F is the real numbers R, the vector space is called a real vector space. When the scalar field is the complex numbers, it is called a complex vector space. These two cases are the ones used most often in engineering. The general definition of a vector space allows scalars to be elements of any fixed field F. The notion is then known as an F-vector spaces or a vector space over F. A field is, essentially, a set of numbers possessing addition, subtraction, multiplication and division operations. For example, rational numbers also form a field. In contrast to the intuition stemming from vectors in the plane and higher dimensional cases, there is, in general vector spaces, no notion of nearness, angles or distances. To deal with such matters, particular types of vector spaces are introduced. See below. Alternative formulations and elementary consequences. The requirement that vector addition and scalar multiplication be binary operations includes a property called closure, that U plus V and AV are in V for all are in F, and U, V and V. Some older sources mention these properties as separate axioms. In the parlance of abstract algebra, the first four axioms can be subsumed by requiring the set of vectors to be an abelian group under addition. The remaining axioms give this group and F-module structure. In other words, there is a ring homomorphism F from the field F into the endomorphism ring of the group of vectors. Then scalar multiplication AV is defined as. There are a number of direct consequences of the vector space axioms. Some of them derive from elementary group theory, applied to the additive group of vectors. For example, the zero vector 0 of E and the additive inverse minus V of any vector V are unique. Other properties follow from the distributive law, for example AV equals 0 if and only if A equals 0 or V equals 0. History. Vector spaces stem from affine geometry via the introduction of coordinates in the plane or three-dimensional space. Around 1636, Descartes and Fermat founded analytic geometry by equating solutions to an equation of two variables with points on a plane curve. In 1804, to achieve geometric solutions without using coordinates, Bolzano introduced certain operations on points, lines and planes, which are predecessors of vectors. His work was then used in the conception of barycentric coordinates by Mobius in 1827. The definition of vectors was founded on Belavite's notion of the bipoint, an oriented segment of which one end is the origin and the other a target, then further elaborated with the presentation of complex numbers by Argand and Hamilton and the introduction of quaternions and biquaternions by the latter. They are elements in R2, R4, and R8. Their treatment as linear combinations can be traced back to Laguerre in 1867, who also defined systems of linear equations. In 1857, Cayley introduced matrix notation, which allows for a harmonization and simplification of linear maps. Around the same time, Grassmann studied the barycentric calculus initiated by Mobius. He envisaged sets of abstract objects endowed with operations. In his work, the concepts of linear independence and dimension, as well as scalar products, are present. In fact, Grassmann's 1844 work exceeds the framework of vector spaces, since his consideration of multiplication led him to what are today called algebras. Peano was the first to give the modern definition of vector spaces and linear maps in 1888. An important development of vector spaces is due to the construction of function spaces by Lebesgue. This was later formalized by Banach and Hilbert, around 1920. At that time, algebra and the new field of functional analysis began to interact, notably with key concepts such as spaces of p-integrable functions and Hilbert spaces. Vector spaces, including infinite-dimensional ones, then became a firmly established notion, and many mathematical branches started making use of this concept. Examples. Coordinate space is the most simple example of a vector space over a field F is the field itself, equipped with its standard addition and multiplication. More generally, a vector space can be composed of n tuples of elements of F, such as, where each I is an element of F. A vector space composed of all the n tuples of a field F is known as a coordinate space, usually denoted Fn. The case n equals 1 is the above-mentioned simplest example, in which the field F is also regarded as a vector space over itself. The case F equals R and n equals 2 was discussed in the introduction above. Complex numbers and other field extensions. The set of complex numbers C, i.e., numbers that can be written in the form x plus iy for real numbers x and y where I is the imaginary unit, form a vector space over the rails with the usual addition and multiplication. Plus equals plus I and C equals plus I for real numbers x, y, a, b and c. The various axioms of a vector space follow from the fact that the same rules hold for complex number arithmetic. In fact, the example of complex numbers is essentially the same to the vector space of ordered pairs of real numbers mentioned above. If we think of the complex number x plus iy as representing the ordered pair in the complex plane, then we see that the rules for sum and scalar product correspond exactly to those in the earlier example. More generally, field extensions provide another class of examples of vector spaces, particularly in algebra and algebraic number theory. A field F containing a smaller field E is an E-vector space, by the given multiplication and addition operations of F. For example, the complex numbers are a vector space over I, and the field extension is a vector space over Q. Function spaces. Functions from any fixed set omega to a field F also form vector spaces, by performing addition and scalar multiplication pointwise. That is, the sum of two functions f and g is the function given by E equals f plus g, and similarly for multiplication. Such function spaces occur in many geometric situations, when omega is the real line or an interval, or other subsets of R. Many notions in topology and analysis, such as contiguity, integrability or differentiability, are well behaved with respect to linearity. Sums and scalar multiples of functions possessing such a property still have that property. Therefore, the set of such functions are vector spaces. They are studied in greater detail using the methods of functional analysis, see below. Algebraic constraints also yield vector spaces. The vector space f x is given by polynomial functions. F equals R0 plus R1x plus Rn minus 1 xn minus 1 plus Rn xn, where the coefficients are 0, Rn are in F. Linear equations. Systems of homogeneous linear equations are closely tied to vector spaces. For example, the solutions of a given by triples with arbitrary a, b equals of 2, and c equals minus 5a, 2. They form a vector space. Sums and scalar multiples of such triples still satisfy the same ratios of the three variables, thus their solutions. 2. Matrices can be used to condense multiple linear equations as above into one vector equation, namely x equals 0, where A equals is the matrix containing the coefficients of the given equations, x is the vector, x denotes the matrix product, and 0 equals is the zero vector. In a similar vein, the solutions of homogeneous linear differential equations form vector spaces. For example, f plus 2f plus f equals 0 yields f equals ae minus x plus bxe minus x, where a and b are arbitrary constants, and x is the natural exponential function. Basis and dimension. Bases allow to represent vectors by a sequence of scalars called coordinates or components. A basis is a set B equals by I of vectors by, for convenience, often indexed by some indexed set I, that spans the whole space and is linearly independent. Spanning the whole space means that in any vector V can be expressed as a finite sum of the basis elements, where the scalars, called the coordinates of the vector V with respect to the basis B, and BIC elements of B. Linear independence means that the coordinates are uniquely determined for any vector in the vector space. For example, the coordinate vectors E1 equals, E2 equals, to n equals, form a basis of Fn, called the standard basis. Since any vector can be uniquely expressed as a linear combination of these vectors, equals x1 plus x2 plus xn equals x1 e1 plus x2 e2 plus xn en. The corresponding coordinates x1, x2, xn are just the Cartesian coordinates of the vector. Every vector space has a basis. This follows from Zorn's lemma, an equivalent formulation of the axiom of choice. Given the other axioms of Zermelo-Fraenkel set theory, the existence of bases is equivalent to the axiom of choice. The ultrafilter lemma, which is weaker than the axiom of choice, implies that all bases of a given vector space have the same number of elements, or cardinality. It is called the dimension of the vector space, denoted dim_v. If the space is spanned by finitely many vectors, the above statements can be proven without such fundamental input from set theory. The dimension of the coordinate space Fn is n, by the basis exhibited above. The dimension of the polynomial ring f x, introduced above, is countably infinite. A basis is given by 1, x, x2, a 40 or I. The dimension of more general function spaces, such as the space of functions on some interval, is infinite. Under suitable regularity assumptions on the coefficients involved, the dimension of the solution space of a homogeneous ordinary differential equation equals the degree of the equation. For example, the solution space for the above equation is generated by E minus x and xe minus x. These two functions are linearly independent over R, so the dimension of this space is 2, as is the degree of the equation. A field extension over the rationals Q can be thought of as a vector space over Q. The dimension of the field extension Q over Q depends on alpha. If alpha satisfies some polynomial equation Qn alpha n plus Qn minus 1 alpha n minus 1 plus Q0 equals 0, with rational coefficients Qn, Q0, the dimension is finite. More precisely, it equals the degree of the minimal polynomial having alpha as a root. For example, the complex numbers C are a two-dimensional real vector space, generated by 1 and the imaginary unit I. The latter satisfies I2 plus 1 equals 0, an equation of degree 2. Thus, C is a two-dimensional R vector space. If alpha is not algebraic, the dimension of Q over Q is infinite. For instance, for alpha equals pi there is no such equation. In other words, pi is transcendental.